There is a set of special cases for which we can directly find a simple expression for the posterior distribution given the data we have. The advantage of this is we avoid calculating any complicated integrals. If the prior p of theta and posterior p of theta given the data are in the same family of distributions, they are called conjugate distributions. As mentioned, this gives us an easy way to directly compute the posterior. Suppose we get multiple rounds of data coming in. In this scenario, we might want to be able to update the posterior every time new data comes in. We can do this by taking our current estimate as a prior before observing each round of new data. I will show an example of this later. Lastly, when using conjugate distributions, we get a closed-form expression of the posterior, and very frequently it's easy to find the maximum value over theta, which gives us a maximum a posteriori estimate. Let's use flipping coins as an example, and we want to estimate the probability of the coin landing on heads. Given data on the coin flips, we want to find posterior p theta given the data, which expresses our beliefs about the coin's weight. Then our maximum a posteriori estimate will tell us what the most probable weight of the coin is, given the data. For this, our posterior and prior will follow the beta distribution, and the likelihood will follow the binomial distribution. Let's start by introducing the binomial distribution. We'll be using this as a likelihood, which is the probability of the data given the parameter. So suppose our parameter is 0.8. The coin is weighted so that it lands on heads 80% of the time. Given this is true, what is the probability that we observe 9 heads out of 20 coin flips? First, we've observed 9 heads of which each head has probability 0.8, which gives us 0.8 to the 9th power. We also observed 11 tails, each with probability 1 minus 0.8 is 0.2. Note that this actually represents the probability of one particular chain of throws. For example, this would be the probability of seeing the 9 heads and then the 11 tails. It is also the probability of seeing the 11 tails first and then the 9 heads afterwards. Since we don't care about the ordering, we need to add up probabilities for all the different orderings of results. There are 20 choose 9 such orderings. In general, for the binomial distribution, we have probability of success p and k successes out of n trials. For our coin example, we considered flipping heads a success. The expression shown is a probability mass function for the binomial distribution. Shorthand for the binomial distribution for n trials and success probability p is binomial n, p. Let's plot the binomial probability mass function for 20 trials and different success probabilities. The x-axis here is the number of successes out of 20, and the y-axis the probability of that result. For p equals 0.8, we see that the probability is high of seeing a result somewhere around 16. For lower success probabilities, we have slightly different shape of the distribution. P equals 0.5 represents a fair coin case. And as expected, if the probability of a success is 0.1, the probability of observing more than 7 is very low. The beta distribution, when used as a prior and given a binomial likelihood, makes the posterior also follow beta distribution. Remember, this conjugacy is what we want to make use of in our coin flip example. The beta distribution has two parameters, alpha and beta, which change the shape of the distribution. If random variable x follows the beta distribution, its probability density function is as shown. In the denominator, we have the beta function. It's related to the binomial coefficient we saw earlier when alpha and beta are integers. I won't go into too much detail on that, but advise the viewer to look into it if they're interested. So what does it look like for different values of alpha and beta? For 1 and 1, we get a uniform distribution. Remember, we use a beta distribution as a prior distribution, so it represents our beliefs about the parameter's theta before observing the data. If we have no reason to believe that the coin is biased a particular way before observing any data, which is most likely the case, we would use this non-informative prior to give equal weight to all possibilities. When we increase alpha, we see more of the probability density concentrated around higher success probabilities. Higher beta values do the opposite. Here's alpha and beta of 5, for which we see more density in the middle. Again, higher values tend to result in a more concentrated plot with lower variance. We can also set alpha and beta to values less than 1, which will put more weight on the edges near 0 and 1. Now, let's prove that if we use binomial likelihood and beta prior, the posterior ends up following a beta distribution as well. This will prove conjugacy. Let's start with Bayes' rule here and expand the denominator using the rules of probability. So probability of the data is the probability of the joint of the data and parameters, marginalized or integrated, over the parameters. Now, we'll just note that our dataset has n trials total, of which k are successes. This means that we can rewrite the likelihoods in this expression using binomial distribution, where probability of success is determined by the parameter, which, if you remember, is the weight of the coin. We take the priors to follow beta distribution with parameters alpha and beta. We can cancel the beta functions in the numerator and denominator since they are constants and the same. We'll combine like terms in numerator and denominator each. Recall that if we integrate the beta distribution, we get 1 since it's a probability distribution. If you multiply both sides of the note shown here by the beta function in the denominator, you'll see that the denominator in the above expression in white is equal to beta function of k plus alpha and n minus k plus beta. We should recognize the resulting expression as a PDF of a beta distribution with parameters k plus alpha and n minus k plus beta. So we can start with prior following a beta distribution with parameters alpha and beta. To calculate the posterior given a dataset of trials, which are successes or failures, we just add the number of successes to alpha and the number of failures to beta, and our posterior will follow the beta distribution with those parameters. Linking back to our coin flip example, let's suppose we don't have any reason to believe the coin is biased either way, so we'll take prior beta 1, 1. Now we observe a set of coin flips with our coin, 4 heads and 2 tails in this case. We call heads a success, so we add 4 to our first parameter and 2 to the second, giving beta 5, 3. Now here's a neat trick. Now that we've observed data, we might want to flip the coin even more and update our beliefs given that additional data coming in. Notice that our belief prior to observing the additional data would be this beta 5, 3. So we'd use that as a prior and find the next posterior given the incoming data. And we can repeat this process with any number of new coin flips. It doesn't have to be just 5 as shown. The beta distribution is well known, so it's easy to find its exact maximum. This is just one example of conjugate distributions. There are many different examples, each to be used for different situations. It should also be noted that not every situation falls into a case where we can use conjugate distributions. For those other situations, we'll have to use other methods.